I'm Christer Walfridsson, and I'm going to talk about my work on formalizing the semantics of GIMPLE. So the work I'm doing is within my project of smtgcc. That is my code for analyzing GIMPLE and assembly using SMT solvers. I talked about this the last year in detail, so I will not say much today, but I will start with 2 slides to just give some context about what I'm doing. So the most relevant part for this talk is the smtgcc TV plugin. So use it to compile your code as usual with the GCC, and if it found some problem where GCC has miscompiled your code, it gives an error. It looks like something like the below. In this case, it has detected that if combine has miscompiled the code in a way such that the optimized code invokes undefined behavior in cases where the original did not. It also gave an example here that if you call this function foo with x is 0, a is 0, and b is 32, then the optimized code invokes undefined behavior, and the original were okay. So how this works is that I set up symbolic values for all input to the function I'm analyzing. So with input here is the 3 arguments, but also the full memory state. So I have both the arguments and all of memory symbolic. Then I go through both the original IR and the optimized IR and sort of emulates or executes the, GIMPLE abstract machine. And after that, I compare the result. And the checks I'm doing there are these 4. That I check that the IR after optimization does not invoke undefined behavior for inputs where the IR before had defined behavior. If that was okay, then I check that both return in the same way for the same input, again for all possible inputs. In the same way, I mean, either return, abort, or exit. For returned values, I check that both return the same value for the same input. And finally, that all the global memory states is the same for input regardless which of the 2 versions you run. And in order for me to do this work, I need all nitty-gritty details of the semantics of all GIMPLE instructions. So that is that I need to figure out what they actually mean, because the documentation is not completely clear for everything. I will make a note here that since I'm doing this work for smtgcc, and there are lots of cases where some details of the semantics does not really affect me for various reasons. For example, right now how I do memory layout means that certain problems cannot happen. But I'm actually interested in getting the full semantics for all of GIMPLE, because partly I'm planning to improve my tool, but also because there are other things I want to do with formal methods and so on. So in order to be able to prove things about various constructs, I really need to know what's happening. So sometimes when I ask things on the mailing list, it may be a little bit unclear if, you can do a workaround, do like this. And it's fine mostly, but I also want to get the full picture. So let's start by looking at some easy part of what I have done. So we start by looking at just these 5 instructions of shift and add, multiplication, and subtraction. So what they are doing is sort of rather obvious. So the only thing in most instructions is to figure out the edge cases. So in these cases, I do not really need to say what happened for a shift. You add the zeros on the low bit and so on. But it's undefined behavior if we shift more than the type size. In C, there are some additional restrictions, but GIMPLE has only this restriction on the shifts. For the other arithmetic instructions here, it's undefined behavior is there are signed overflow, at least if the type says so. That's one thing that is sort of annoying with GIMPLE, that it changes a bit depending on what things you pass to the compiler, but that's all. Nothing to do about this, just to deal with it. But that's also something I need to specify in my formalization and try to figure out which flags affect everything. Vector instructions of this have the same behavior element-wise. And the reason for this is that we can, in some cases, split the vector into scalar instructions, and then we need to preserve the semantics. When we talk about undefined behavior, there are essentially three reasons why you want to have undefined behavior in the IR. So you may have operations that does not really work, so they might trap and so on. So division by 0, for example. Different architectures may give different results for the natural instructions. So shift, typical case for that. And also that making certain things undefined behavior may enable more optimizations, such as the overflow for signed addition. But there may be, when creating the semantics of an ISI, there may be other alternatives to making them undefined behavior. We could say various ways of returns an arbitrary value or that kind of thing. So there are alternatives. So that's good to keep in mind for certain cases. And let's say undefined behavior may enable optimizations, but it may also make perfectly fine optimizations invalid. So let's look at this example. That was the one I compiled on the first slide. So it's two if statement return 2 if they are true, otherwise it return 0. In this case, the if conversion has transformed it to the version to the right. So if you look here what's happening for the case that my tool gave us for the first case. So x is 0, a is 0, and b is 32. So the first function returns false on the first if statement, and it returns 0. Nothing bad happens. But the optimized version starts by shifting by 32, which is undefined behavior. So this was an invalid optimization. But this optimization is actually fine for all hardware that GCC support, as far as I know. It could fail for certain hypothetical hardware that always returns -1 if it's shifted too much. Because then you can get cases where you return 2 and it should be 0. But otherwise, here is a case that perfectly fine optimization got forbidden by the undefined behavior. This is one bug that I reported that happened a lot when doing fuzzing. I'm not sure if that happened in real code, but anyway. Here, the SLSR pass has done strength reduction. These are the ordered instructions that so one of the multiplications become a multiplication by 2 instead. And this reassociation means that it may get different overflow than the original. If you run by 2 on the original here, you will get some values where this happens if you want to verify that. So in this case, it's the same result, just with undefined behavior, so it's okay. But it's easy to modify this, so it actually gives the wrong result. Essentially, if you have an if statement by 0 under this in a certain way, then expand can do things that give different result. There's some academic team doing quite a lot of fuzzing that has triggered this several times and reported that are getting linked to this ticket if you are interested to look at that. None of these are fixed. No, that is open. As far as I know. This was another shift thing got fixed. Yeah. I'm not sure if this is an interest. It's more for completeness. I took one example with vectors also, where one vector element makes a difference. Because in this case, the SLP vectorizer has changed this to load B and C as vectors and add both, subtract both, and then swizzle the results to get the elements it's interested in. So, but that makes it do additions and subtractions that were not in the original. So for example, if B1 and C1 are both max int, then you get a new addition here that overflows, but the original did not have anything like that. All of these overflow things are in general easy to fix by just casting them to unsigned in the optimization passes doing the work, but it's very annoying to do. And my final example here is this loop. And after IV optimizations and so on, we get the thing on the right. That if you look at the variable 58 at the top, it calculates the IV for the next iteration. So we can have a case where the original loop had no problem, but because the problem only happens in the next iterations. But here we do it a little bit too early. So for example, if you pass this with the start that is max int minus n, you get this problem. So this particular case can be fixed also by casting to unsigned. But where it happens most cases is for pointers. So if it's happened quite a lot in our test suite where we have various things where accessing pointer with a stride. So if you pass a really large stride or and so on, and an iteration count of 1, then nothing happens in the first version because the stride is never applied. But in the optimized one, it applied and can overflow. So it's kind of thing that probably will never cause a problem in reality, I guess. But my tool finds it quite a lot because it tests all values. So all these strange combinations that nobody would care about are detected. Then, if a little bit philosophical question about what is GIMPLE, it's not just a GIMPLE statement. The compiler has lots of data flying around, collected from various places. Most of that is just what is in the IR, but in a nicer form. But there are some cases, for example, VRP. So if you take this code example here, that has a built-in unreachable. So on the original GIMPLE, it looked something like this. The VRP pass eliminates the unreachable and puts the information in the range of data. So far, so good. So now we have this. And phi opt does this transformation, because vopt knows from the range data that the value must be 3 or higher. But this that is nothing that is written in, if you look at the GIMPLE statements. So in some sense it's not strange, because this is, from within the compiler, it's definitely possible to find this data from the GIMPLE statements. But when we talk about the work of formalizing, it's not really obvious all the time exactly what data must be tracked and what must I take advantage of in the formalization. So smtgcc looks at all the range data also, but there are probably other similar things that are missed at the moment.
But you can see the VRP details if you use the corresponding flag to fdump GIMPLE.
But does it print that for each pass? I only think it does when it's changed.
Yes, it does print for each pass for all the SSC names. It prints above it a comment where it says it has this range and this mask and.
Okay.
And that's the global data, which is, I think, yeah, the only interesting thing for you in the dumps, because some passes enable the ranger and it does during the pass, and it looks only at the branches and so on. But that's part of the pass internals. But this kind of VRP is preserved across different passes, so it's part of the GIMPLE, which is interesting.
Okay, yeah, thank you. So let's go to the less basic stuff. So memory. So we start with, we have discussed this a little bit on the mailing list. So the conclusion, well, my interpretation of the discussion is that pointers are just integers, but with provenance. So there are no restrictions on alignment and whether they point into an object or whatever. So that is different from C. Here we are permitted much more. And that is, for example, if you look at the vectorizer, it usually creates vectors that point a bit after the vector to check if everything fits within a vector, if it's done with looping and so on and so on. So lots of things will break if we change this. Pointer plus, this undefined behavior if it overflow occur, unless it's passed with flags that say that is okay. And it's also undefined behavior if the result is 0 and the input pointer and offset are not 0. So null plus 0 is okay, but otherwise the result cannot be 0. When we access memory, so it's undefined behavior unless all of these 5 things are true. So the access must be in bounds, which actually is more complicated than what it might sound. The rest of the presentation will be about that. The pointer provenance must be correct for the object that is being accessed. The pointer must be correctly aligned. It's a bit unclear for me exactly what this means in GIMPLE. I'm using get object alignment, so GCC tells me what it expects, and I just check that the pointer is like that. But from my point of view, it will be good to actually have clear rules. This is what alignment means. For store, the memory must be writable. And we must satisfy the type-based aliasing rule if strict aliasing is used. And again, for the rest of this presentation, I will assume no strict aliasing because we have enough problems as is with the other rules. So first things with being in bounds. This is maybe not that strange because I think several of the POSIX instructions actually require this, but at least that's how they are used in the resource. So when you have a structure and access a memory in that structure, the whole structure doesn't need to fit into the memory you have. It's only the part you are accessing. So that's not that strange. And you get similar thing for bit field ref because the compiler can change a component ref to a bit field ref. So you get things like the line below that sort of access one of the first elements in the structure. But if you look at what the vectorizer does, so if you take this function and compile it for x86 v2, so the vectorized code start by doing one element at a time until everything is 16-byte aligned. Then you do one vector at a time. And the final load here may be out of bounds, but that's perfectly fine because since it's 16-bit aligned, we know it must be on the same page. So we compile these extra elements, but the epilogue take care of and check that it's only the elements that is in bound that are being used for when returning the result. So everything is fine from an assembly point of view, but we now break this part of we are not reading. We are reading out of bound here, so this is obviously undefined behavior. So what I did in smtgcc is that I change semantics. So for vector types, I do it slightly differently. So the first element must be in bounds and follow all the rules. And the out-of-bound element must be on the same page as the last of the in-bounds elements. That works well enough, but there are some problems. So let's look at this stupid example. So here we have an example, a variable x that is aligned. So we can read a vector from it with this semantic. And we read a vector here. So everything's fine. It returns a vector where the first element is 0 and the rest are, well, whatever happens to be in the memory after it. If you change the function like this, now we have a dead array there where I've written some data, but a dead store. So the compiler eliminates this. But this could have been within the unaligned, well, the out-of-bound part of the original, in which case the return value would be 0, a couple of uninitialized element, and 3. And now when this is removed, it changed the result. So this elimination is actually an invalid optimization with the semantics are specified, because the compiler cannot know that this array isn't aliasing with the vector load. Some people look confused.
It just means it's not a good semantic of the out-of-bound access.
Right, so it's from a semantic point of view, is you can explain.
So it's basically an example that your workaround for the earlier issue is not a good one, right?
Yeah.
Because this is a counterexample where that doesn't work.
Right. Or my workaround could be a good one, but then we need to go and change other passes.
So, right, so at the beginning you said there are other options. So currently we say out of bounds is undefined behavior. If it said out of bounds is arbitrary data, then it would be still fine for both.
Sort of, yeah.
Talking, for instance, from the C++ point of view, where the C++ 26 is changing stuff, they have the erroneous behavior and indeterminate behavior. So maybe, and actually it's not undefined behavior to copy an initialized variable from one place to another. If you are copying it using memcopy, or if you are copying it using unsigned char, or make any kind of char or nested byte or something. And so maybe you should create it immediately as undefined behavior, but just mark the byte or part of a vector element as indeterminate, and only when you actually use it for something else than copying into some other place. If you copy it to some other place using chars, then just copy the flag.
Well, but
This field or element is initialized. This one is not initialized. And only when you actually use it for something else, so cast to a different type, or
Like here,
or
checking at 0.
yeah, comparison, addition.
but
That's all undefined behavior in C++, but just copying around is fine. And I think in C it's the same case, because you do it all the time. You create a structure, the padding, you copy around all the time.
It's theoretically risky with floats, because they can have trap representations with the digit defined for you.
right. But if you look at this example here, the vectorizer actually has generated code that reads out of bounds data and then do this comparison. And so it always actually does some work on it.
So it would be undefined behavior of the vectorizer. We want to avoid that.
So, but I think
The question is if you're using masking for it, or if you do comparison and then don't care about what the comparison results for this part.
So the whole point is we can't use masking because it's early break. We are doing alignment to ensure it doesn't travel. But it's still undefined behavior.
This looks a bit similar to what Valgrind tries to unravel when it suppresses dynamically during execution that you have accessed undefined memory and then a conditional bound on that.
So I would say that actually I come back to your points in 3 or 4 slides, but there are more problems. But you're right. And actually how smtgcc right now handles uninitialized memory is more or less exactly as Valgrind. There are problems with that also. That I cannot talk about today, because actually my first version of this talk actually talked about that instead of what I'm talking about now. But I couldn't get it in a form that actually was understandable. And it needs more time than one slot.
A variant of it I've run into is that Valgrind says it's undefined behavior if you branch based on an uninitialized bit.
Yeah.
But it doesn't stop you, for example, streaming the uninitialized bit over the network or writing it to disk and then having something else depend on it, which a normal person would probably consider a bug.
Right, but you still have an uninitialized bit in some padding that are completely fine. So that is why smtgcc must handle that, because otherwise it reports undefined behavior on all padding that gets, or that the memory has changed when the padding has changed for various reasons. So, but go back to, okay, yes, so we are still on this semantic right now. So here we also have a bitfile ref. This is one example from the test suite that, well, anyway, we have a vector mask here. So with our semantic now, it's okay if this mask if it is correctly aligned. It's okay if the first element is defined and the other ones are out of bounds. And the IR that gets created is something like this. So again, it reads this mask to the vector 1, and then gets the elements. So far, so good. But then forward prop changes to this. Now we have bit field ref that reads out of bounds, completely out of bounds, which is undefined behavior according to the earlier discussion. So here forward prop did something wrong, which may or may not be a bug in forward prop, but as we have discussed, our tentative, semantics is not optimal anyway, so it's probably that is the problem here. But anyway, this is something that smtgcc currently complains about. We could update its semantics a little bit, say that the out-of-bounds elements are essentially treated as padding. A hand wave exactly what that means now. But essentially that they get the value and that value is sort of arbitrary and it can change if you read it several times and whatever. That makes the things we have talked about before mostly okay. So this also, we can update the bit field ref in the same way that if the full element it extracts from is within bound, then the extra bits may also be these padding kind of bits. There are some open questions about how should we handle elements that are only partially in bounds and so on, but we can skip that for now. But this is not enough, because the store merging pass can change bit field refs like this to single copy using unsigned long. So it's not only vector that we need to handle. We must handle other types too. And the semantic I proposed before was that each element needed to be inbound. But here we have the unsigned long and only part of it is inbound.
It's a big property.
Yeah, maybe. It complicates a bit how we want to, when we talk about how defined these padding bits are. When do they do undefined behavior and so on. But sure, that is possible to just treat them as bit properties and do it bitwise. Annoyingly, it makes my tool much slower, but well, that's life. I must do what the compiler expects. But this doesn't work either. Because if you look at this example, so this is now defined if we call it as foo with the address of C. So it reads now, provided that C is correctly aligned. I forgot to add an alignment on it. Because this now returns 0 and the rest are these padding bits. But here the store elimination pass eliminate the first store because it knows from the aliasing system within GCC thinks it cannot alias because it's 8-bit value cannot aliasing with a 32-bit value. Or rather, reading a 32-bit value cannot come from the 8-bit value. But I have disabled strict aliasing, but it sees that you only have 1 byte and you read 4, so it doesn't fit. So it's not strict, so it's not type.
Kind of a point of provenance trick based on size. So it's a point of provenance trick we do based on size, which helps quite a lot with if you turn off strict aliasing. Or breaks this case.
More levels of no strict
No strict provenance.
But we get more problem. If you look at this example, I've compiled it for ARM. Then the vector code checked if P1 and P2 are 32 byte aligned. And in that case, it processes 2 vectors at a time. So now the second vector can be fully out of bounds. And again, so as in the previous cases, after it has found them, if it finds that this if statement is true, then it goes in and checks that everything actually was in bound. So it's perfectly fine result, but it can now read very much out of bound, and that breaks our tentative semantics here. And here I don't think I can propose any workaround, because from if you look at the GIMPLE side, you see a load from something that is not corresponding to anything. So that if you say that this in some sense is okay, then load from address 2000 is also okay from a semantic point of view. And you can get other problems with that, there are other variables after, and you get lots of provenance problems and whatnot.
So when you go one step further and say the constraint is only the load may not trap when it didn't trap before, like with the alignment thing.
Yeah.
And it produces, when it's out of bound, it produces arbitrary data, which in fact it does. But in the end, of course, the flow, like the return value, or whether it calls exit or not, that may of course not change.
Yes. I'm thinking about what kind of problems it may cause. The problem is if we find another variable in this, then it will be provenance UB.
If it's only a read, I mean, yeah, as the program doesn't change when the value changes of that out of bound read, that's the constraint basically we put in. It doesn't matter if it violates provenance with something else, because it can only change the value, and that doesn't matter.
Right, but you have 2 variables here. We have the first that we are doing our vector operation from, and then we have the other variable here. And now we read after the vector and get this. The problem is, how do GIMPLE know that if this is a continuation of the first or if this is a separate load of the others? Because that will affect dead store elimination and everything like that. How do you know that?
As the dead store elimination would be valid to do it or to not do it, because it may only change the value of that load where the value doesn't matter. So it doesn't change the program behavior. So what it changes is the global memory state, of course, because we did that store elimination, but that's not undefined, right? It's just an optimization. So you would have that issue anyway.
Okay.
So basically it's like treating it the Walgrand way. So it doesn't matter, you have loaded some undefined things, you branch on it, and even that may depend on the thing, but the outcome of the branch may not depend on the actual value.
Right, but the problem here is how to actually restrict it in a reasonable way, because here you are comparing it, you are branching on it and so on. So how do you know that it doesn't affect this? It is fine if it doesn't affect the final value, but how can we see it from the semantics that it does not?
So yeah, basically if you would have a series of branches and the actual path you take doesn't matter as long as you reach the same side effect statements, right? Well, I'm not sure if that's expressible within the smtgcc thing.
It sounds very fishy from a semantic point of view if you say that here we have a program, it means doing this, and But yeah, I see what you mean. I think the devil is in the detail, and I think we will get a problem specifying this uninitialized data in a suitable way. But I will give it a try and see what.
So you would basically have to, at each of this kind of point, it would be an additional input that would vary over all possible values, right? It possibly explodes your iterations.
But I would guess that it is possible to do some interesting things where we get different variables and code motion and aliasing and so on. But I'll give it a try and see what's happening. So yeah, this was my last slide. So my conclusion here: GCC performs valid optimizations that are invalid under the GIMPLE semantics, or at least SMTGCC's interpretation of the GIMPLE semantics. And I think there are inconsistencies that in any way, and it's not completely clear how to resolve this. And that was the end of what I had.
So first of all, thank you very much for doing the work and for uncovering all these issues, which are actually not only academic, because like with, as you said, with the vectors, we eventually lower them into scalars, and then we actually miscompile code. So you can, in some cases, it's difficult to create test cases that are actually miscompiled, but all of these things are real bugs, and it shows how. Yeah, but it shows that undefined behavior is both good and both very bad. So how do you propose we start to document semantics? Like for the loads and stores, is it good to document GIMPLE semantics in terms of constraints before the statement and constraints that still hold afterwards? Because like all these ideas we floated around, I'm not sure if you can express that in a way that it completely describes an abstract machine. Like producing an arbitrary value is not a good abstract machine description. So how do you propose we try document this? Because I think it's important to try document this, or even document limitations that exist now.
Right. So I have been fighting with it myself, because my plan is to document my understanding of the system, because it's sort of both because I think it's good to specify exactly what SMTGCC does, so others can review what I have done and see that you are wrong there. But also because there are things I cannot handle, and it's good to state exactly what SMTGCC handles. But I have not really managed to do a really good way of writing it yet. So I don't know is the best answer.
So like there was a time, I think GCC 5 time, where I last revisited how we do type-based aliasing, like where we started to treat each store at starting new lifetime of an object, and where I kind of put some section into the internals manual documenting the GIMPLE memory model, I called it at that point. It's possibly not the correct term other people would use for memory model. So I think there's a whole section in the internals manual on GIMPLE itself, and so obviously that would be a good place to start documenting things, especially what exactly is undefined in GIMPLE, and more specifically where we make use of that undefined behavior for optimization, because like we do differ in details from the set of languages we support, but of course we have to make sure to not make things undefined in GIMPLE that are defined in the languages.
Oh.
Or we have to put in workarounds like for Fortran with the shift of exact type width, which is defined in Fortran, but not in GIMPLE.
Right, and also as you said that C++ is doing work with this, what does undefined really mean and how to restrict it and so on and so on. And I'm not sure that the current GIMPLE does everything exactly like that. So I think
the patch is not merged yet. But it will work pretty much like the ftrivial out of our init option. So basically we have an internal function which says this initialize this variable or this memref to something which is well-defined, constant, if it's at runtime, but it still causes warnings for uninitialized uses and so on. So the idea is, yeah, that if you read it multiple times and compare, then it should compare equally. If it's undefined behavior like normal in C and so in C++23, then we don't guarantee anything. And if you compare it, read it twice and compare, then we do. Sometimes they are equal, sometimes they are not equal. Depends on what you compare it against. And so yeah, the intent is to make it reliable at the expense of some runtime.
Isn't the ARM 9.5 example with the vectorizer actually a bug because 9.5 has MTE? And that means the granularity for permissions is just 16 bytes, not 32 bytes, or 4K pages.
okay, so here it has checked that the pointer actually is correctly aligned.
Yes, so that the pointer's alignment doesn't work with MTE. Tamar said that, and well, he's not happy about the fact, obviously, but there's no solution. But I mean, there are the first fault loads, which would save you because they apparently happen to interact with MTE correctly. But yeah, it comes at a cost. So don't use MTE.
So any more questions? So I have a big bunch of other similar small issues that I will start sending to the mailing list the coming weeks. So we'll see what's happening with that. But I hope you now have got some idea about why I'm doing stuff and what kind of things I'm focusing on. So I think it can be easier to discuss how to resolve them after. So thank you.